Okay, welcome to Lab 6, Newton's second law. And what we're going to be observing is a system with a cart attached by a string to a hanging mass. And that's going to go over a pulley. And so what we want to do is determine the acceleration of both objects. And there's a few things that we know that will help us do that. So the hanging mass is going to be falling down, and so you know there's going to be some net force down on it from gravity. But what else is acting on the hanging mass? And while it's falling, you'll notice that the string is tense. And so there is some tension in the string pulling up on the hanging mass as well, which is attached to the cart. And so that force comes between the hanging mass and the cart. And so if we look at just the hanging mass, we know there's going to be some weight down, mg. We know there's going to be some force up due to tension in the string, but we don't know what that tension is. We just know that it's there. And so the net force acting on the hanging mass is equal to ma. So in this case, we're not in equilibrium. So the sum of the forces is not 0. The sum of the forces is equal to ma. And so our net force, ma, is going to be equal to the tension, because the force is going down, it's in the same direction as mg. And so we're going to get negative ma, because it's going down, is equal to tension, which is positive because it's pulling up, minus mg, which is going down. Now, when we look at the cart, it's also going to have an mg acting on it, but it also has a horizontal surface under it, exerting a normal force up, because we know the cart itself is not falling down. You can see it now. It's not falling through the track. And so you can't say, so the sum of those forces, since it's in equilibrium in the y direction, is going to be 0. So we're only concerned with the x direction of the cart. And what is the only force acting on the cart? Since we're not giving it a push ourselves, the only thing acting on it again is the tension in that string between the hanging mass and the cart. And so for the cart, the net force, ma, is going to equal just tension in the string. And so we can use what we know about how the force on the cart equaling tension, we can plug that in into the equation on the hanging mass, where negative ma of the hanging mass is equal to tension minus mg. And for that tension, we can plug in the force acting on the cart, which we know is ma, or mass of the cart times a. And the last piece of the puzzle is, because they're connected by a tense string, we know that they have to be accelerating at the same rate. So the m of the hanging mass times a is the same a as the m of the cart times a. So in both net forces, that net acceleration is the same. And so now the question is, what can we do to figure out any of those pieces? So we can figure out g, and we know m of both objects, and so we can rearrange that equation to solve for what we expect a to be. But of course, in lab, that's not good enough. We want to experimentally show that a is what we think it is. And so today in lab, what we're going to do, a little differently than normal for you, is I'm going to film the cart going with the various masses it says in the lab, 5 grams, 6 grams, 8 grams, 10 grams, 12 grams, and 15 grams as the hanging mass. And we're going to measure how long it takes to go there. And then we're going to use kinematic equations, which I'm sure you miss and love, to determine the overall acceleration on that interval from yellow, there's a yellow gate on one end, to the yellow flag here. And so that distance is 1.5 meters. And we're going to use the distance and the time to figure out an acceleration of the cart, which we also know is the acceleration of the hanging mass, and use that to compare it to what we know by manipulating equations, and to show, hopefully, that physics works. So again, what we're going to do is have you time videos of the cart moving, being pulled by the various hanging masses. and you're going to solve for A using kinematic equations, and then you're going to compare that A to the A you found by manipulating Newton's second law. So that is what you're doing going forward. Good luck, and hopefully some of that made sense. If not, feel free to listen to it again. All right.